Welcome everyone to another episode of our Coffee Breakdown podcast. Today we have with us Jorge González, who is a postdoc at the Differ Institute. He is working mostly on scrape-off layer and edge plasma modeling, particularly on linear devices. So welcome to the podcast, Jorge.
Hi, thank you for having me, Aaron.
Yeah, it's a pleasure to have you here. Actually, so one of the reasons we decided to bring you in this time is actually the last episode we had Renato Perillo on, and he was discussing your topic, but more from the experimental side. So edge plasmas, how to do experiments, and how it works from that side. And I remember him saying something about that at the state of things are right now, it's sometimes better to just do the experiment and see what you see. But of course, you work on the modeling side, numerical and theoretical modeling. So I imagine there's a lot of interplay between these two. And I wanted you to explain, let's say, the same field, but from your point of view. So first, what do you do? How do you use these models? And how does it tie in with experimental observations and experiments in general?
Okay, so focus is on trying to simulate MAGNUM-PSI, which is the plasma linear device that is operated at Differ. It's quite unique in the world. It can mostly replicate the heat and particle flux that are expected at either Divertor, so that is something unique. There is no machine in the world that can do that right now. So that is a particularity. But the important thing that we are trying to do is to use the same tools that are used in typical scrape-off layer and edge modeling for tokamak. Main tool is called SolPS Ether, which is a code that has been used for decades. And what we want to do is to use this tool and apply it to a linear device as unique as MAGNUM-PSI, which is not easy. But why we want to do this is because then first we can validate the code against MAGNUM-PSI, which is much faster than doing for a tokamak. We can extract more information both experimentally and numerically than from a tokamak. And also because then we know that if we see some effect, some dynamic, both in the plasma and the neutrals, if we are using the same code, this is validated with experiments, we know that we can translate these informations to a tokamaks divertor. So that is a huge point to have a similar code, to have a small and simple machine as MAGNUM-PSI compared with a tokamak, and be able to extrapolate information from one machine to another.
Okay, and do you think, I think this was also a comment by Renato, that there are often large differences between linear machines and tokamaks. Like there are regions where they are the same, and then there are regions where they are not. And the question is, how extrapolatable are these two in your experience?
Well, that's a good question. When you go to a linear device to try to start information for a tokamak, you are only looking at like the last leg from the divertor. You have these magnetic field lines that impact your divertor and transfer a huge amount of heat and particle fluxes. So you really, in a linear device, you can only focus on the last part. First, because of the geometric difference between the two devices. So this is something that you cannot replicate in a linear device. But also because what you really want to see is how this plasma will interact with the target and the neutral that are in that region. And that is usually something that is complicated to obtain in a tokamak device, because the divertor is not a region easy to access. Sometimes it has a very specific function to remove heat from the device and to not contaminate the core, to pump away the the byproduct from the fusion reaction. So you really don't want to mess too much with that part of the machine. You don't really have viewports that can easily access or only that region. You always have to go to other part of the device. But if you can have similar densities, temperatures, and fluxes, you can really say, okay, I have this influx of plasma to a material. We usually use tungsten, but we are also testing more strange things. So at least what you can get from a linear devices, at least from simulations mostly, is, for example, what are the relevant atomic and molecular process? Because when you have this plasma impacting to the target, it will transfer a lot of energy, but also the ions will get recycled at this target, and they will become neutrals, and these neutrals will interact with the plasma, and that is also an important thing on how to cool this plasma. So you really can extract information, and if you know which process are relevant, or how to increase the amount of collision process that appear, that's something that you can extrapolate to a tokamak divertor. If you are testing a device to reduce, or some idea to reduce the heat flux to the target, to the divertor, you can test that into linear devices. You can do an experiment that will give you a large amount of experimental data, because MAGNUM-PSI and in general linear devices, you can access a lot of information, a lot of different diagnostics. And then simulations will give you a lot of additional information about mostly collisional process. It can give you information where diagnostic cannot reach. And that information, that the important information, that set of relevant process, or how impurities behave, or how to reduce the heat flux, can be translated into a tokamak.
I see. Okay. And so in a way, the linear devices allow for smaller, quicker experiments to be run about fundamental processes happening close to the material surface. Like, because one of the, I guess, questions was that these processes, or at least in the tokamak, the plasma source in some way is dependent on what's happening at the surface, because then the impurities flow back and they change your plasma beam, your incoming plasma. But in a linear device, these are usually separated, right?
Yeah,
from each other.
that's something also that because from Magnum conception and design, it was designed to operate completely independent from what happens to near the target, to near the source. Now we are starting to think that maybe this is not true for all the cases, because we are doing simulation that show that this might change, and we are planning experiments to behave that. But well, you can check a few things that will happen upstream and how this will affect the plasma, but it's not the object of a linear device. Linear device, at least MAGNUM-PSI in particular, and other devices in the fusion community, are planned to, okay, we want to see how this plasma will interact with this surface. And there is a lot of physics happening in this small region that is important. You once that, for example, when we work with lithium, as one thing that we are trying to achieve is to have lithium in a porous structure, expose this to a plasma, and one way that the plasma will lose energy is by evaporating this lithium, because it has a melting point relatively small, so and have a low evaporation pressure, so it will get evaporated. It will form a cloud that will also assist in radiating away energy from the plasma, and that will be a way to reduce the plasma energy. When we do that kind of experiments, the amount of diagnosis are limited because of this lithium cloud. So in that point, we have to also go back to simulations to see what's happening. And one thing that we want to know is these lithiums will get charged, will get ionized. Are they being transferred upstream the plasma beam, for example, because that is an important thing regarding impurities, and this can also happen with another impurity. So we can study this kind of dynamics. We cannot study from the complexity of the full divertor leg in a tokamak, but we can provide estimations on this. That's another thing that can be done, but the focus is more near the target, what's happening, how the plasma chain, can we really, we have a plasma from in the conditions of ether, can we really mitigate it completely, can we detach it just by introducing neutral particles to extract energy from the plasma. Those are things that can be studied with a linear device like MAGNUM-PSI, both experimentally, of course, but also with simulations.
Yeah, exactly. Okay, so we pretty much covered, the differences between linear devices and tokamaks, but on some sense, it was also what you brought up was that simulations allow you to see things that in an experiment you can't, because there's just a limit on the types of diagnostics and also what those diagnostics can actually measure. So in that sense, maybe you can explain a little bit how these simulations, like what in these simulations give value back to the experiments in terms of what extra variables they can see and how you interpret them.
So, for example, one thing that is difficult to see experimentally, because in a simple hydrogen case, in MAGNUM-PSI, you will have ions, hydrogen ions. You will have atoms of hydrogen neutrals, but you will also have molecules and molecular hydrogen. And when you introduce additional gas for a detachment, you do it in a molecular way. So one thing that simulations can show, which is not easy to obtain experimentally, is how these molecules and atoms interact with the plasma, because they have different way of iterating. For example, an easy difference is a molecule that is composed by two atomic hydrogens can dissociate because the interaction with mostly high energy electrons. And that is a process that doesn't happen in atomic hydrogen, of course, because you have nothing to dissociate.
Right.
And those are things that if you can obtain it somehow experimentally, which is extremely complicated because you have to measure distribution of atoms in density, temperature with an extreme accuracy. You have to take into account an exact amount of the amount of gas that you are injecting, pumping away, which is almost impossible. In the best condition, you will be able to do it in a point in one slice of the plasma, and that is not good because you want to see what happens in the whole volume of the plasma, because you have interactions in a large region. And for example, some experiments that especially those based on lasers or light basically have issues when you try to look close to a material, because you have reflection, for example, and so you have to have perfectly aligned lasers. You have to try to avoid the interaction with the surface. So it's not easy to obtain information of things that are happening really close to surface. And those are situations in which simulations, because usually you need to get the real dynamic of the thing, you have to simulate a huge volume, much more than the points in which you can measure. Simulations give you the whole device, so you can extract information from each point you want. You can go as close to the target as you want, for example, to see what happens there. One thing that, for example, was being checked is, okay, you have an ion that interacts with a surface, this recycles it into a neutral, but then the neutral gets ionized again by the incoming plasma, and it can enter in a series of cycles happening millimeters in front of the target. That is really difficult to measure. So you really need to go to simulations to see what happens in this dynamic, for example. And as I said, for example, when you are in these cases that you are evaporating a metal like lithium or tin, which are two that we are mostly trying, you are limited to diagnosis because you have this additional species which adds a lot of unknowns to the case. Also, lithium especially tends to deposit in a lot of the viewports of the device, so you cannot access those quite easily. So if you constrain your experimental access, or just because of how your experiments are set up, you can only look at that point, you really need simulations to check what's happening in the rest of this point. Experiments will allow you to look at one region, but simulations will allow you to look at the whole, which is important.
So in some ways, because also these different species, you want to also know not just are they there, but where they're coming from, right? And if you look only at a single point, you can see how much is there, but you don't know why, right?
Exactly.
You're limited in that type of information. And so the simulation sort of expands how much you know.
Yeah.
Okay. Now the question is, it seems like a very complicated problem you're working on, right? There's plasma, then there's normal neutral gas, then there's different species, and then there's the interaction with the wall. So there's a lot of factors happening to make the scenario or the physical phenomenon that you're seeing. So these codes, then these simulations must be incredibly computationally expensive, or at least complicated. So how do you go around working with that, right? Is there certain simplifications that can be made, or do you really have to go down to first principles for everything?
Well, there are a few things. The first simplification that we do, which saves a ton of computational resources, is that we assume that the plasma is a fluid. Yes. This means that the plasma behaves in a way that is closer to a high density gas, which is or a magnetized high density gas, which is an awful simplification, but but this allows to use a different set of equations that simplify the computational requirements. That's and that's a good point. But we have the issue of these neutral particles, which don't behave like this. They don't follow this fluid approximation. So for that, we have to go to kinetic model, which basically look at the particles almost individually and follow the trajectory, and then these particles interact with the plasma via a different set of collisional process. And for that, you need the second big assumption, which is okay, at which rate or how these particles interact with this plasma. You need to have information about collision cross-section. We mostly tell you how often this collisional process happen, but you also have to take into account how energy involved in this collision is distributed among the particles, which are the products. An atom can get ionized, a molecule can get dissociated. A lot of things can happen that we have to include, or at least we have to cover the most basic process that we think that are relevant, or that we have information, which is also a limitation, because these calculations and these measurements of collisional rates and cross-section that are required quite delicate, and not everyone knows or want to employ decades in obtaining this data, which is another important thing that we have in the fusion community for modeling, that we need data that nobody things that nobody wants to obtain, and it takes really a lot of expertise to get this data. So that is another important assumption. The third one probably will be how these particles interact with the surface, which you could do dozens of theses about this topic because it's an infinite topic. You have a lot of process that can happen. In fusion, they seems to be constraints to the ones that affect for this high density plasma. The obvious one is sputtering, in which you have a high energy atom also or an ion impacting a surface, and then an atom of the material of the surface just gets sputtered away. So that is an important one. That it was especially quite relevant when tokamaks had carbon walls. Now it seems that with tungsten it's not so relevant, but still important. And as we go up in power, it will increase. We will need to also take this into account. But really, the treatment of the walls is relatively simple. I'm also working and collaborating with a group in Italy, which is trying to do a model to couple with these edge codes to try to improve how these targets are treated and try to put more physics into it, because we really will need to know. Because okay, you simulate your plasma, and you know, okay, I have a heat flux to this material, and okay, I finish my work. But that's not true. Behind that, you have you need to a way to extract that heat because you have cooling systems. You need to check erosion, because especially if you want to extract energy from a tokamak, this will operate for a longer time. So these are things that you have to take into account in a way. And now we are starting to look into it more in deep. So that those will be probably the three basic assumptions that we are using. This fluid plasma that is fully magnetized, this collisional process between neutral and plasma, and this treatment of the materials on the surface of the device. And with that, you can put together very complex codes that take all of these and 1,000 parameters into account, and they give you a solution. The thing is, how do you trust this solution? And this is when we have to go back to experiments, to validation, to reevaluate the physical process, if what the assumption that we are taking into account are valid or not. And this is mostly an iterative process that just go in circles until we are able to extract some data.
Okay. Yeah, the validation of your models are, of course, incredibly important. And that's true. There's a big circle there on between simulation and experiments, right? Like the experiments need simulations to understand what's happening, but then the simulations need experiments in order to validate the model, right? So it's like
it's
infinite loop.
It's a vicious circle that nobody knows how to break.
Yeah. Well, I think there's no way to really break it. You just, as you say, just keep iterating until they converge, right?
Yeah, you just
hopefully they converge.
Yeah, you just kind of have to validate with some things, and then expand the experiments with another thing that your code can produce. You, for example, we are when you go to experiments, you try to validate with macroscopic parameters that the experiments give you and the code give you. And then you say, okay, then this means that for these conditions, my underlying assumptions are valid. And I can, in these conditions, I know that I can expand, and the information that the experiment give me, I can expand it with some comfort. It's if I'm in these parameters, I know that things will behave so and so. But yeah, if you move outside these parameters and you try to predict what's going to happen, you will never be sure until you validate again, and then yes, the circle just goes on and on.
Yes, because there's so many different, like the complexity of the code is so high, and so many things can change when you just want to move to a different like plasma regime or something, or change the wall or what, that it becomes impossible to even say with certainty that the translation between what you know and where you want to now run it is valid, you know. Okay, that's true. But I think also one of the things I want to come back to that you mentioned is these collisional processes, this atomic cross sections, also even the materials problems with like heat transfer and stuff like that. These are concepts that are not fusion specific, right? They cross over into many, many fields. So obviously, I would assume that in these codes that we are already utilizing the knowledge from these other fields and also returning. It's a way of having, let's say, the work that we do in fusion mesh with other, you know, industries and research around the world that is not fusion specific. So in a way, do you think that fusion really helps to push forward these concepts, especially for these specific materials we're using? Or do you think that it's already sort of someone else is interested and we just take their data?
There has been during the decades a lot of data, particularly for collisional process, that has been done for fusion, and it's still being done for fusion that can expand because to other fields. Because in fusion you are most interested in hydrogen, heliums, and isotope of hydrogen mostly. So you need data in a wide range of parameters. But nevertheless, plasma is any plasma physics is quite multidisciplinary, and you can always get some information from another field of plasma physics and either contribute to new information or obtain new information. And I know in terms of collisional process, there has been a lot done. And now in terms of materials, now that we are looking to particularly the next generation of fusion reactors that hopefully will produce net energy and electricity and will save the earth.
Hopefully, yes. That's why we're all here, right? Working on this, yes.
then you have to start looking at lot of material. There is a lot of material size in fusion field from how this material will sustain this. So just analysis of defect in the materials, damage by neutrons. You have a lot of people working on that, and how we can create new materials or new structures to mitigate this damage. How these things will translate to different fields, there is translation between these fields, obviously. Might be that because the fusion community has a clear objective, it might not be that interested in other fields currently, because of the objective of the fusion communities is quite clear. But I really think that fusion is always looking for other solutions that might help, and other communities, particularly in plasma physics communities, should look into fusion, because you are doing things in a wide range of parameters, of temperatures, densities, and there is a lot of learn and a lot of information to exchange. And I'm sure that materials and concepts that are being tested for new tokamaks and will be used in the future for all things I know, because there are people at Differ that they are trying to use the same plasma parameters that are used in fusion scenarios, for example, for microprocessing, microprocessor manufacturing, for coating or materials with a surface, or doing modifying structures by exposing them to a plasma, which is you have also a huge industry working on that. It might be that in the past it was not economically or it was not easy to achieve the conditions for the plasma in a reactor just to apply for an industrial process, for example, because it was not worth it. But now that the fusion technology is evolving and we have to evolve, we have to improve these additional technologies, these linear devices to generate plasma, something like that, it might be that all of that will end up dripping outside to other fields, and that is good. Maybe as a community we should try to go a little bit farther, but yeah, we do what we can.
I do admit it sometimes, yes, like fusion, we have a goal and it's very, we're focused on that.
Yeah.
And in some way, that is all right, in the sense that we push this. And if there are other people looking in that see some data of value or some research of value, then of course, I think most people in fusion are quite open to discussing, right? But yeah, as you say, we don't really search them out on our own. But it's nice to have that cross-pollination. I always find it's interesting to talk to people from other fields to, sort of see if what we're doing is useful to them, plus also if they have a solution to a problem that we have, they've already developed. These are things that are very cool to keep your eyes open for and your ears open for. And I think in such, like, especially in your work where there's so much complexity and so many different processes involved, it's maybe easier or more advantageous even to do that, right? It's because it's almost impossible to put everything together on your own.
Yeah.
You might as well get some people who have already experience in that particular aspect to help.
Yeah, particularly in the field of plasma surface interaction or plasma material interaction. There is a lot of cross knowledge from yes, material science and engineering that now is coming. It started coming for ITER because ITER needed a whole new set of materials for operating, and now is starting to come in. And I think that when we improve the understanding of how a plasma will interact with this material, that will open the possibility to treat to do other things. I don't know. I remember there was a talk at Differ a few weeks ago. I think it was a person that was using a plasma generated at Differ to create nanostructures in nickel, I think.
Oh, okay.
For electrolysis, because then you increase the amount of surface exposed to water mostly, so you can make better electrolysis, and that is a good thing. We improve the knowledge of how this plasma interact with the surface, and we can do new applications for this, and that is quite interesting. And the thing is, okay, but can we learn more, and can you go back to your previous steps and say, okay, I have now learned this, we can review this other thing. It's sometimes this is when you start doing research, as you know, you never know when you're gonna end up.
Yes.
But yes, as we have discussed, when you work in fusion, you have a clear objective, but obviously it's good to deviate from that somehow. Maybe you cannot do it as much as you want.
But it's good to have some flexibility.
But
right?
yeah, and it's good to always keep eyes and ears open. try to learn new things, try to just get all the information that you can, because you never know what's going to be useful.
Yeah, that's a good point. And I think this is a good way to transition into your personal experience. Of course, this field that you're working in is not only, as we've mentioned, complex and diverse in terms of the physics and the technologies involved, but it's also quite cutting edge in the sense that a lot of people are still not sure exactly what's happening, or not, it's nothing is really fully defined. There's of course a large body of knowledge already, but there's still a lot more to learn. And so how does it feel to be really working on that edge, sort of like where really nobody you talk to knows the answer? We're all speculating and seeing where it goes.
Well, I've never felt that way, honestly.
Oh, really? Okay. You feel there's always someone who knows.
No, I mean, I think that maybe for tokamaks in the past, they were not. The Divertor was something that was there to just remove things and make the tokamak work. As power increase and device become more complex, you had to start thinking about this Divertor a lot. And from that, you got devices like TCB, which usually try different configurations for this Divertor, and that spawn a feel of, okay, we have to look into what's happening. We have power laws that are reaching the limit of what the best material can sustain. How are we gonna avoid that this important part of the machine melts? Because if this breaks, we can no longer operate this machine, especially if we want to operate this machine for hours. If you have a shot in a tokamak that is a second or 5 seconds, okay, yeah, whatever. But if you really want to go to a power plant and you want to operate this continuously, you really need to understand this. So that's say, okay, we have this extremely complex and extremely involved region. We have to look deep into this, and this is for me is an extremely interesting problem. Is especially if you look at from the point of view of MAGNUM-PSI, in which you kind of can forget about the most complex plasma physics that happens in a tokamak. You just focus in this small finished part, so you can focus really on interaction with the walls and interaction with the neutrals. Then it becomes a really beautiful problem that really big question is what is happening. That's the big question in almost all research. But here is, okay, I have this condition. What is really happening? How are my molecules affecting? Because for decades, molecules didn't play an important role in devices, but now they will play an important role. So how can we put all of this knowledge together and extract some useful information? And that is a really important problem. It's also quite frustrating sometimes. Maybe it doesn't get the full attention that deserves from the fusion community at some points, but because there are other more interesting things to explore in the core and and things like that.
Perhaps, but perhaps no. I mean, there's been a lot of shift of the focus into the, well, pedestal physics, and then also scrape-off layer physics, and then the divertor region with detachment and vapor shielding and all this stuff. I think that the focus is slowly shifting there, but that's because it's goal-oriented, as you said.
Yeah, exactly.
Right? As you build a power reactor, a reactor that will produce net energy, these things need to be solved. We need to understand them, or else the machine just, it will work, but it won't work as well as we want it to, right?
Yeah, and if if you had a lot that tungsten could support, it will matter much less because your problems will be reduced. But even ITER will operate at the limits of what pure tungsten can hold, can stand. So even for ITER, we will start seeing some issues. It might not be a big problem because ITER is still an experiment, so you can just stop it. You can even remove the divertor if you want. I think that they have a few of these, just removing the divertor and putting a new one planned. But yeah, if you move towards the next generation of devices, especially with these small devices that are running in the United States, this Spark device, which you are taking a huge power and making it in a much smaller region, so your power density skyrockets. And I think that they still don't know a solution for that. At least I was not provided one that was.
I think they were looking at the Super X thing with the flux expansion and stuff like that. Right?
I've heard Super X, that is that you have your divertors extended long time. I have received answers about weird ways to just mostly take the walls of your tokamak and just substitute for new walls.
Oh, really? Like on the fly?
I have heard ways that you will immerse this into a, like, not a bucket, but let's say a bucket of a liquid metal that you can just chain when it's needed. So that was one of the last solution that one of the last answer that they gave me in a conference, which was interesting.
This is the vapor box concept.
Not exactly.
Not exactly. Okay.
No, it was not the vapor wall, because this was mostly not for the divertor. It was mostly for the first wall.
Like liquid walls. Somebody was saying this to me before. I didn't fully comprehend them. Did you? Did you?
No.
Okay.
Because then you can take these liquid walls and just put it away and put a new one. It was like I don't know. It sounds quite weird to me, and it's an interesting concept. But they say that this will be in like 10-15 years, but I still think that they have some issues with that. But happy to see how this evolves.
Yeah, it takes some creativity, right? If everybody tries a bunch of things, maybe one will work.
Nothing against new innovative ideas. If they get the funding and if it works, it will be amazing. Whatever. But I think that there is also an issue from a concept to having in operation for a power plant. And that is what's happened. That will be a big change from ITER to the next reactor demo.
Yeah, that's true. I think there's a lot more discussion happening even in the fusion research community now about things like availability of the reactor, design for maintenance, right? How often does it need to change? How often do we need to shut down the reactor to change things?
Can we have humans to change things, or do we need robots? Because of I mean, if a few scientists die, nobody cares. But if maintenance people start dying regularly,
that's not
will
good
be
for
an issue.
That's not good for PR or whatever.
So yeah, you have to start shifting your point of view, as you said, to other things, and that is where your divertors become important. This is where you have to talk about your liquid divertors. You have to talk about the vapor box that you mentioned, which is another thing that I'm working to have working at in MAGNUM-PSI, because that hopefully will be a good way to reduce the flux towards the divertor. I have my hopes up for that.
Okay. So yeah, I guess that's a good thing to ask then, in your personal opinion, like which of these diverter concepts or technologies do you think is going to be the most
okay.
feasible one moving forward? Just your opinion.
I might be
Yeah.
a bit biased because as I'm working with a vapor post concept to test in MAGNUM-PSI and see that it's working. But the main thing is that you need to have a large amount of neutrals to reduce this plasma energy, this plasma flux. The issue is if you have a lot of neutrals, then this escape to the core, and that reduce the temperature of your core, and then you have just have killed your fusion reactor, and then you don't have a fusion reactor anymore.
Right. Yeah. You don't have plasma anymore.
Yeah. So the simple way to do this is, okay, let's design something that retains as much as possible these neutral particles, because then this will allow you to reach high density of neutral particles that will reduce the plasma energy. And if you reduce the amount of particles that are escaping up to a level in which they don't affect the plasma, because you can have different chambers, or you can have a chamber and then pump these particles away in between different chambers. That is things that have been planned for other things. Or for example, if you have a metal, a vapor of a metal, then this metal, you can make it condensate into the walls, and you can try to recover it and clean it and add it to the device, to this vapor box again. So I really think that this is extremely good concept to reduce the heat flux, because the issues with these Super X configurations is that particularly, okay, they look good when you look from an steady point of view. So okay, you just take your divertor leg and you make it as long as you want, as far as you can have the magnetic configuration for it.
Right.
Okay, then and then you need to worry less about the contamination of the core. Okay, good, but as at least most of the work I have seen about this from a numerical point of view is related with steady state simulations and how this operate. What will happen when your divertor legs moves and is no longer controlled? I think that here we could start talking about the controlling of the magnetic field, which I have no idea. So better not to start talking about that. So the thing is, how you control that is much more complex than just having a lot of neutral particles retained. So in my opinion, the designing of divertors, you can call it vapor box if you want, you can call it a closed divertor, will be much more important to mitigate these heat fluxes. Just take this incoming flux, recombining and distribute it along a larger surface that is your closed box. And in there you can have more neutrals, or you can introduce these metals to have a different process. So, and you can, if you can do that without affecting the core, without particles escaping to it, or a large amount escaping to the core, then you can easily control, because you can estimate how much gas you need to put, or how much metal you need to have. There is still some things to check. I'm working on simulation for the MAGNUM-PSI concept for the vapor box that we are designing. So things that we want to see, a part of how much is the plasma cooled by this vapor box, is how much lithium is escaping this box. We can also check how much is this box being heated up, because that is also an important thing. But yeah, I mean, as I said, maybe I'm biased, but I think that this is a good concept to have in mind, and it's a relatively simple one.
Yeah, and it's good to also believe in the concepts that you're working on, right? Otherwise, why are you working on them? Right? I don't think it's a bias, but this is almost a necessary one, I think, in
Yeah.
research, right? Okay, that's cool. Yeah, because like there are lots of different ways. As I said before, it's the field of the divertor and the scrape off layer is starting to become more relevant, or at least getting more attention from the fusion community at large. And what used to be considered, I don't know, outlandish ideas, like very strange, people are actually starting to consider them a bit more seriously now, because they realize that our current solution, which is the standard diverter, is just not, it doesn't work as well as we want it to, especially if we move to power reactors. So
Yeah, the current divertors are usually referred to as trays. So yeah,
as what? Sorry,
astray.
ashtrays.
Yeah. So yeah, they have a function. It's not a pretty one. But if you want to move, you need to start thinking about sometimes weird ideas. But who knows? You have to throw things to the wall and see what stick. Here at Differ, we are trying to test this paper box. I know that the TCB are mass upgrade, and other devices are going more to this different configurations in the Divertor magnetic field, which I have nothing against, of course. But also that influence the design of your device a lot. So let's see, maybe in the end it's a combination of a lot of factors, as usually happens. Maybe we need to do a little bit of this, a little bit of that. Maybe for some situations we need to have liquid metals, maybe for other we don't need that. Maybe we just need to have a truly complex machine that has a lot of solutions, and we will need a lot of people from control system to determine which solution will be better for each scenario.
Yeah, I think, and with that, I think we are slowly approaching on our time. So thank you again, Jorge, for joining. And yeah, just to remind our audience out there that Coffee Breakdown is a podcast where we're mostly focused on the human side of science. And it's good to remember that not only are we hope that you're learning from all of these discussions, but that we, myself, and all our guests are also in the process of learning. So thank you all for attending, and we'll see you in the next episode. Bye.
Bye, everyone. Thank you.